So in this lecture note, we will study about multivariate distribution and spherical multivariate normal distribution and spherical normal distribution. So let's learn some definitions and notations first. First, we still consider, you still have a random vector y, which is an n by 1 of dimension n by 1. And each of the yi's here will be random variables. So that's why it is called n-dimensional random vector. So in general, it can be a random vector, or if we append random vectors, it becomes random matrix, is a vector or matrix whose elements are random variables. So if they are random variables, we can find the expectations of random variables. So the first definition here is an expected value, which we usually denote by E of y. So the expected value of your random vector y is the expectations for each of the y1 to yn. And by notation, we will denote the expectation of y1 as mu1, and so on and so forth until the expectation of yn as mu(n). Or in general, if you see this notation mu, this is a random vector of your y, of your yi, of your yi's, denoted by mu i's. So pag mu lang class, that is a vector, n by 1 na siya, where each component will be the mu i's, or the expectation of your yi's. Mathematically, you can solve the expectation if your y or your random variable is a continuous random variable by getting the integral of y and then its probability density function evaluated dy. Or if it is discrete, this integral sign here will be substituted by the summation sign. So y, and then the probability that your y is particularly equal to your big Y, or that is the probability mass function. So for continuous random variable, f of y is usually called the probability density function. For discrete, so this is continuous. For discrete, your probability density function is usually called the probability mass function, and usually it is denoted by the probability that your capital Y is equal to a small y, so mass function. So the next concept that we learn is the covariance matrix. This is a symmetric and square matrix. So covariance matrix is a symmetric. Symmetric matrix is a matrix where the transpose of it is just equal to A, and then it's square. So usually the covariance matrix is either denoted by cov of y or the capital sigma notation here, wherein the diagonal entries are the variances of y, which in other notation can be written in this manner, and the off-diagonal entries are the covariances here. So since it is symmetric, kana siya more or less is the same as the entries here. So these are just two notations of your sigma. You can expect it to be written as this, or sometimes it is written in this manner. So note that the diagonal entries or the variances of the yi can be written in terms of covariance, but it is the covariance with itself. So yi. Unlike the covariance of two random variables y1, y2. So if it's when I is not equal to j, it is usually covariance of yi, yj in general. And then the covariance of yi, yi is actually the variance of yi. So in general, the covariance or the variance of yi can be written as sigma ii, and otherwise, if yi is different from yj, then it is sigma ij. In terms of expectation, the covariance is actually the expectation of y minus mu times y minus mu prime, or computational formula, you can solve the covariance by the expectation of yy prime minus mu prime. So in general, if we are talking about covariance xy, where x is distributed as mu1, na siya distribution iyaha, and y is mu2, then the covariance will be the expectation of x minus mu1 and then y minus mu2 prime. So if they have the same distribution, all of them are mu, so mu rani siya and then mu rani siya. So it's the expectation of x minus mu and y minus mu prime. Okay, so this is the general formula of your variance in terms of expectations. So in your basic probability class, you know that the variance of x is the expectation of x from its division square, and it is computed as x squared, the expectation of x squared minus the expectation of x quantity squared. This is familiar to you in the univariate case. So observe that if we have in the multivariate case, this square here will be a prime. So kung kuha ko variance sa x, that is the expectation of x minus mu times the x minus mu prime, no, in the in the multivariate stage. So kini siya, may lisa na siya ani. Okay, and then this term here will be changed to its primes. So ang mga square din will be substituted by its primes. Do you follow? Are you still there?
Yes, ma'am.
So kini siya akong gi-square din is the usual that you see in the univariate case. In terms of multivariate case, that will be changed in terms of primes. Okay? So let me write it in a proper way. So here, this is the multivariate case scenario. So in your multivariate case, if x is just univariate, so this is just x minus mu square, which is the expectation of x square minus the expectation of x quantity square. So in terms of multivariate case, so mahimo na siyang expectation of x minus mu prime. And this part here will be expectation of x prime minus the expectation of x times the expectation of x prime or mu prime. Okay. Right. Okay. So I hope I'm understood with that. So this known results which I selected will be useful when we prove Arnold in the later theorems and lemma. So these are obtained in the book of Rencher, chapter 3. So equivalent sila kung unsay chapter 2 mga concept na nasa Rencher chapter 2 ginagamit sa concept sa Arnold na chapter 2. Concept in chapter 3 are also will be used also in chapter 3 of Arnold. Okay, so in this lecture notes, this is theorem 1.4, but in Rencher, this is theorem 3.6a. So let A be n by 1 vector of constants, and Y is an n by 1 random vector with mean vector mu. Okay, so if we make a new random variable, which is linear combinations of your random vector and some vector constant, or vector of constants or constant vector by notation, that is a prime y. So ang imong a prime is actually ang pahigda because your a is the prime of that. So patindog yun ang a, no? Paana na siyang a. So it's a column vector. So if you get the prime, it becomes a row vector times your column vector y. So a prime y is kana siya times that will be the sum, which is this, no? The sum of ai yi, I from 1 to n, so which is this. And if you get the expectation of this new random variable, which is the linear combination of your random vector y, it's just equal to, okay, this is by substitution of your x, which is a prime, which is equal to a prime. Since that is just a constant, you can take it out of the expectation and just get the expectation of y. But by notation, expectation of y is mu. So the expectation of x, where x is a prime mu, is just equal a prime y is equal to a prime mu. Okay. Next. So suppose we have several linear combinations of y with constant coefficients. So suppose you have x1 will be a11, y1, or in general you have the summation of a ij a1j y j, no? J from 1 to n, or that is just a1 prime y, and so on and so forth. So your vectors of constants is this, and this is your random variable y. So these p linear functions can be written as, say, x, which is equal to a matrix. You can define a matrix A and your random variable y. So your x here are these components. So x1 to x2 to xp, and then your ai's here can be written in this manner, but this is actually these row vectors, A1 prime are row vectors of this form. This one are row vectors of this form to cater these coefficients here, no? Kana siya. And so on and so forth. And you have your random vector y. So if you try to rewrite this matrix here, if you try to rewrite it as ay, kini siya, i-multiply ani, so kana plus times ana will generate this linear combination, and this is equal to this, no? Are you following?
Yes, ma'am.
Yes, ma'am.
So kini siya times kana, mao ni mo gawas. Okay? Which is equal to this. So that is just transforming your linear combinations into matrix notation, no? This is your matrix notation. So ang matrix notation, isuat na nimo as kanang A times imong Y. And this is your X. So X is a vector of x's. Your A and your Y will produce this one. Okay? So typically, the N is less than P with the rows of A to be linearly independent and so that A will be of full rank. Ang atong gusto, the number of, because for it to be linearly independent, dapat ang mga columns din will not be expressed as a linear combination of the other columns. So we want N to be less than P. For X to be full rank and X prime X to be invertible and X prime X inverse to be to exist, no? So later in the application in regression analysis, you see there that y is equal to x beta plus epsilon. We want this x here to be full rank so that x prime x will be invertible. X man x prime x, because you will see later na to compute your beta hat in terms of this design matrix here, kining A, later kining A ninyo mao ni ang x sa imuhang estimator na beta hat. You will see that this is equivalent to x prime x inverse x prime y to compute for your beta hat. So dependent siya ani. So kinahanglan ang atong design matrix X there is full rank. So that X prime X will be invertible and X prime X inverse to exist. However, in regression, usually satisfy na, but in ANOVA, the design matrix there will not be of full rank. There are linear dependence on the entries of your design matrix. So that's why we usually add constraint when we do ANOVA. So if you are familiar with ANOVA, na mga constraints ang ANOVA, you subject the linear combination of the parameters equal to 0. But actually, pwede po ka maghimo imuhang constraints depending on your problem. Okay. The next theorem in the second reference of by Rencher will be this. This is basic in your probability class. So if you have y, a random vector, x, a random matrix, and AB are some vectors of constants, and capital AB are matrices of constants, and assuming that matrix multiplication is conformal, then the expected value of AY is just equal to, so you can put out A outside, expected value of the transpose of a vector pre-multiplied to X, and B, a vector of constant post-multiplied to X. So will just be equal to this. So what you will get is just the expectation of your random matrix. And if you have this, still the expectation of AXB is just A times the expectation of X times B. So expectation of a constant is just equal to a constant. No? So all you have to get is just the expectation of your random variable or your random vector or your random matrix. But for variances, this will not be straightforward. Okay, so let A be a P by 1 vector of constant and Y be a P by 1 random vector with covariance of matrix sigma. So ibig sabihin, Y or the covariance of Y is equal to sigma. So that if you form a new random vector, say X, which is equal to A prime Y, so you know that this is the summation of AIYI, no? And then if you get the variance of your X or a new random variable of the form A prime Y, then this will be equal to A prime times the variance of Y times A, no? Or that is A prime sigma A. So we have dili lang siya distribute ang variance diha. So it is pre-multiplied by A prime and post-multiplied by A. So in terms of variance, sa ganina sa expectation, murag isuod lang nato ang expectation sa ato ang random variable. But in the variance, it's not. Okay? So for the proof, if we use the usual definition of your variance, so that will be equal to, so again, if you recall, the variance of X is equal to the expectation of X minus mu quantity squared. So doing that with X equal to A prime Y, so you will have A prime Y minus A prime mu square. And then common factor is A prime. You can take it out of the parenthesis there and you have that. And then as what I have said in terms of multivariate setting, X the square there is actually equal to XX prime, no? So what happened here is that you have A prime times A Y minus mu, then Y minus mu prime. A prime is distributed to all of them. So this should have prime here. Okay. So if you distribute that, that is A prime Y minus mu and A prime Y minus mu prime. Okay. So this is this part. And then this part here can be written in this manner. correct? Because this is just a constant. A prime prime for a constant is just a constant, and you can put the constant there. And then from here, you see that this part here, you can, this is just a constant, no? So pwede na nimo isulod ang expectation, not distributed for all kini na term. You can take the expectation of that, but by definition, that is the variance of y. So that will be equal to a prime times a. Okay. So this part here is a prime and duha ka a minus mu, and then this is distributed in that. So mao ni may tabo. But a prime y minus mu is just equal to y minus mu prime a. Pareha na sila. If you recall, the inner product of uv is equal to u prime v or v prime mu. So this is what happened here. So okay ra ito. So from here, this is a prime y minus mu, y minus mu. And then you have that. Okay, u prime v is just equal to v prime mu, which is this part. And the result. Okay. Are you still with me?
Yes, ma'am. Unsa kay ning kuan, ma'am? Kaning summation of A basta variance of Y na lang nabilin?
So to?
Kaning summation of A ang result sa expectation aning Y minus
Summation of A. Ay, summation
kaning
of
sa
A.
last na ano,
This
ma'am?
one?
Oh, di ba variance of Y then nanoyana na ang notation mabilin.
We denote sigma as the variance of Y.
Okay, sir.
Here. Dili na summation, sigma na.
Okay. Thank you, ma'am.
Nara. Na.
Okay.
Isa to nangutana?
Di na, ma'am. Thank you, ma'am.
Okay na?
Yes, ma'am.
Dili. Kinina notation, it's not summation, it's sigma. Okay?
Okay.
So mo nang usually dili na ko ibutang summation din he. Awa na. Wala na ako gisam kay ang na ako'y ginagamit na sigma sa ako ang variance, covariance matrix. Okay? So dili ni siya, kinina notation is not summation but the variance of y. So this is equivalent to a prime variance of y because this is y minus mu, and then a. Any questions from the other? So no questions. So as a corollary to this result, if you have another vector, kay kanina isa ka vector naman na siya, no? So equivalently, how do you rewrite this? In terms of covariance, this is the covariance of a prime y, no? But this time, you have another vector of constant b prime. So instead of a here, it will be equal to b there. And again, this term here is the variance of y. This is the covariance matrix of y. So let y be a p by 1 random vector with covariance matrix sigma, and a and b are p by 1 vectors of constant. Then instead of having a there, you will have a b there. For the proof, similar to the previous example. So let us do this. So these are your assumptions. A and B are vector of constants, which are p by 1 in dimension. Your random vector also is a p by 1 with covariance matrix sigma. So the variance of y is sigma. And you have to recall that the covariance of xy will be something like this. Of course, both x and y here will have a mean mu. They have a common mean, that is the assumption on this result. And the variance of y is, by notation in multivariate case, is equal to that, which we denote by sigma. Okay, so kung sa univariate case, I really want to emphasize this, na sa univariate case, for random variable x, ang variance is just x minus mu squared. This is the usual notation you see in your probability class, but in multivariate case, it will be in terms of transposed of vectors. So using this result, so you have there covariance A prime, B prime. Substitute this. And this time, you have that. Factor out A prime, you have this. And then in here, if you apply the prime, so din ang naitabo, nara sa B prime, pero sulod pa siya sa transpose, no? And then, if you apply the prime, it will be equal to y minus mu prime. Kini prime ani. Man kining B ni mo will be y prime prime. No? So you have that. And then now you can apply expectations, since A and B there are vector of constants only. So apply expectation inside, but by definition, this is your variance of y, which we denote by sigma. So you have A prime variance of y, or sigma b. Okay, are you still with me? Internet connection is okay?
Yes, ma'am.
Okay, next. Here, we will take the result without proving it. What this theorem is talking about is that if we assume that y is a p by 1 vector with a mean mu, and we do a transformation on y by renaming it as x, but the transformation will be pre-multiplying it by a matrix k by p. So this should be conformable. A is k by p and y is p by 1. So the new random vector now is a k by 1 random vector. And then you have a transformation again on y by pre-multiplying it by m by p matrix. Y is p by 1. So this w now is an m by 1 vector. Okay. And your vector y is having a mean vector mu and covariance matrix sigma. Then, if you get the covariance of this transformation, this is equal to A times the variance of y, which is sigma, times A prime. So this is just a generalization whenever in this proof we have a transformation that is just pre-multiplying your random vector by constant vector of constants. In this next result, this is a transformation pre-multiplying your y by a matrix of constants. So similarly, they have the same result except that it is pre-multiplied by your matrix A and post-multiplied by your transpose, the transpose of A. And for this particular example here, wherein the transformation on Y is two variables. One is, if this is your X, A prime Y, and this is your Z, which is B prime Y, then the covariance of XZ will be equal to that. This is a vector of constants, but this time this will be matrix of constants. So similarly, you have more or less the same result, except that tanawa ang diferensya. What's the difference? So when it is vector, when the transformation on your random variable is pre-multiplied by a vector A prime, inaani lang, or A prime sigma A, no? If it is the same vector. However, for matrices, ang transpose na asa, so sa vector A prime sigma A, pero sa matrix is A sigma A prime. Sa vector A prime sigma B, pero sa matrix it's A sigma B prime. Why is that? Because this is just the matrix as a whole. The difference here is here, we did a transformation na transpose. So actually, maora na result. Kaya lang, transpose man din eh. So may mo siyang transpose mo nang matangtang ang iyahang transpose din he. Pero ang ato ang sa matrix, wala man nato gi-transpose ni. Kaya kung ato ning gi-transpose, bali ang transformation is A transpose Y, pareha ang result. May mo siyang A transpose sigma A. But the problem, dili pwede na A transpose. Why? Anong dili pwede A transpose?
Kay di na siya ma'am conformable, ma'am.
Okay, because it will not be conformable as how we defined A to be its dimension. Okay, kay may mo man siyang P by K, man ang imong Y kay P by 1 man. So, dili na siya conformable. But actually, the result is the same. Kaya lang sa vector A prime man gud atong gigamit dito. Do you understand? Kasabot ra?
Yes, ma'am.
Okay. And then, if we have linear combination, so ang atong transformation gihimo sa y na kay bag-o na variable x say ay plus b, mao na atong pag-transform. So take note, ang atong ginabuhat dinhi na kay random variable y, gina-transform lang nato na kay a prime y, mankuhaon nato ang expectation, kuhaon nato ang variance. Na kay ay, kuhaon nato ang expectation, kuhaon nato ang covariance. Karon mag-transform na punta sa iyaha. So x say x star. Mag-transform na punta sa iyaha na ay plus b. So of course the expectation of x star will follow from the linearity of expectation will be equal to the expectation of ay plus the expectation of b, which is equal to a expectation of y plus expectation of b, which is just a constant, is b. And if the expectation of y is mu, so a mu plus b. That's the expectation. In terms of covariance, this is equal to a sigma a prime. So what happens here, murarag siya covariance of ay plus covariance of b. You can do this because if we are sure that ay and the constant b are independent. But since this is just a constant, so you can do this. But the constant of the variance is just 0. That's why the covariance of ay is just a sigma a prime. Okay, so take note that the transformation of x here is ay, so the result follows. And in here, if we are having two different transformations on y, then we should have a covariance of x and y. Let us denote it by sigma yx. So ibig sabihin, the covariance of xx or just the variance of x is denoted by sigma. Pwede xx or just simply sigma, no? So mao na ang mga previous notation na to. But if we are dealing with two different random vectors here or random, okay, x and y here are defined as random vectors, q by 1 and n by 1. So y is an n by 1 vector, x is a q by 1 vector, so that it has its corresponding covariance matrix. Then the covariance of this transformation, ay and bx will be equal to this. So instead of talking about the variance of y inside or sigma in the previous result, ang naa nato ana sa una kay the covariance of ay bx is equal to by is equal to a sigma b prime. This time the middle term there or the middle matrix there will be the covariance of x and y. Okay. So with that having in your mind, we can now prove lemma 3.1 of Arnold. So lemma 1.13 is lemma 3.1 in Arnold. So in Arnold's notation, he started with a random vector x. This random vector x has a mean vector mu and a covariance matrix x, sigma. So your x has a mean and a variance of this notation. A is a matrix of constant and B is a vector of constants. And then we do a transformation of X. X taha, and we denote it by Y. So the transformation of X denoted by Y will be AX plus B. And according to Arnold, the expectation of this transformation Y is A mu plus B. And the covariance of Y will be A sigma A prime. For the proof, by assumption, you know that your random vector X has a mean mu and a covariance sigma. So the transformation Y is equal to AX plus B, which is this one. Linearity of expectation, you have that one. The expectation of a constant is just a constant. Previous result that if you get the expectation of a constant matrix of constant times the random variable is just equal to the matrix times the expectation of X. But we know that the expectation of X is equal to mu. So the expectation of Y will be equal to A mu plus B. And to solve for the covariance, using theorem 1.10, the result of on Rencher. So if we look at that, uh, 1.10 here, if you get a transformation, something like this, that is equal to that. So this is equal to this. You can do this linearity because B is just a constant, but that is not true whenever you have two random variables. This is not equal plus. That will not be equal to when dealing with two random variables na. For example, na kay X plus Y na. That's not necessarily equal to the covariance of Y plus the covariance of X. No? This is not true whenever there is no set assumptions on X and Y. But you can do it here because B is just a constant. Pero kung two random variables na, dili na tinuod. Na ay conditions. Else, you have to find the cross products of the covariances. Anyway, you will see results on that later. And here, this is equal to this by the previous theorem, and the covariance of a constant is just 0. So we have this result. So note that this part of the lemma proves the corollary in the previous discussion, corollary 1.11. Okay. So typically, when K is less than or equal P, and you have a matrix A which is K by P, when this is true, then we say A is of full rank. And if A is in full rank, then A sigma A prime will be positive definite. So if it is positive definite, that is positive definite, and sigma is also positive definite. Otherwise, kung dili na tinuod, kung greater than P si K, remember K and P are the dimensions of your A, then non-negative matrix ra siya, no? You have A sigma A prime is non-negative. Now, we usually want the property of a positive definite because later if you are going to, in the formula, if the inverse is needed in the computation, and if it is not positive definite, then the inverse will not exist. No? So usually gusto ta sa property sa being a positive definite matrix. For sigma to be positive definite and for sigma inverse to exist. So kung dili ta sure na positive definite si sigma, problema ta sa sigma inverse. Okay? And then in the computation of many statistical methods, it always has the inverse of your covariance matrix. So it is very important that A sigma A prime for any matrix A should be positive definite for sigma to be positive definite. Okay. So the expectation of the square norm of X. So this is the inner product, no? Or actually, the square norm of X is actually your X prime X. Or X prime X. Or X prime. No? Okay. Kanang square norm of V is actually the inner product of V. So which is equal to B prime V or B prime B. Now this is wrong. B prime B ra jud siya. Or X prime X lang. Kaya ang kung VU siya, VU square norm, it is V prime U or U prime V. But since this is just the same V, it's just B prime B. So this is X prime X by notation, but X prime X, ihatag at dimension sa X sa taas. Random vector na siya, no? Basta ang X prime X dapat conformable. So, for this to be conformable, dapat square matrix ni. Kaya kung N by P, P by N, conformable ng yapon. It will result to a square matrix. So, this is a square matrix. If you look in details the entries of your X and try to compute for X prime X, dinha ang row dinhi, okay, ang row dinhi, ang X na to ang row dinhi mahimong so kung naapoy X, naay mga rows para na ibutang sa X prime kana dinhi mahimo na siyang column dinhi. Are you following? So mahimo na siyang column dinhi. So mag X prime X ka unsa may imong i-multiply the same entries. Okay? Ito i-detail na lang nato para makita ninyo ang X prime X. So kung naapoy X na 1, 2, 3, 4, 5, 6. This is 2 by 3. So ang akong X prime will be 3 by 2. Which is 1, 2, 3, 4, 5, 6. So kung kuha ko X prime X, this is 3 by 2. This is 2 by 3. May mo siyang 3 by 3. So, x prime kana times kana. Are you with me? So that will be 1 square plus 4 square. So, and then kini times kana. So may mo siyang 2 square plus 5 square. 2 square plus 5 square. And so on and so forth. You can do that too. So mao ni may tabo. Summation of xi squared. Okay lang? So kana. And then linearity of expectations, you have that. Okay, so if you recall in your univariate case, the variance of x can be computationally derived by looking at the expectation of x squared minus the expectation of x squared, which means that the expectation of x squared is equal to the variance of x plus the expectation of x quantity squared. So if you look at that, the multivariate case, so pwede na siya as the variance of xi plus the expectation of x quantity squared. Okay? So until this step, that is okay. And then distributions of summations and expectation of x is mu i's, and then you square that. So that is mu I square, and then summation of the variances. So summation of the variances, if you look at your covariance matrix here, sa gani ang sulod ani, di ba? 1, 1, 2, 2, to n. Are you with me? And then kini mga combination na, sigma 1, 2, sigma and so on and so forth, sigma 2, 1. Okay? So kung mayroon kag summation of the variances, which is the summation of this, is actually the trace of your sigma. Sa gani ang trace, by definition, the trace of a matrix of A is the diagonal entry or the sum of the diagonal of the A's. Correct? So kining summation sa mga variances is actually equal to the trace of your sigma. And this one, by notation, can be mu prime mu, which is the square norm of mu. Questions? Question? Are you still with me?
Yes, ma'am.
Do you have
Ma'am.
questions? Ha?
Ano po yung dimension ng yung result niyo, ma'am?
Sir, anong yung result ko?
Ang
This is what
trace
we want
of,
to show. Ha? This
di
is
ba
what
ma'am
we
ang
want
x
to
mo, ma'am?
show.
Okay.
Okay, what line do you want to, you did not understand? Let's number this.
Ma'am, ang x, ma'am. Di ba ma'am random vector na siya, ma'am?
Yes.
Yes. So ano siya, ma'am? Like q by 1 or n by 1, ma'am?
X is a random vector. There's no specific dimension, basta as long as when you do vector and matrix multiplication, it's conformable.
Okay.
Basta X is assumed to have a mean vector mu and a covariance matrix sigma. So any operation here or any transformation here should be conformable. So when we multiply AX there, dapat conformable si A o si X when you do multiplication. And whatever is the result, that will be the dimension of Y. So for example, your X is n by 1. So your matrix A can be P by N or can be N by N. And then your vector here should be kung P by N siya, butang nato hindi siya square. So your result here is a P by 1 vector. So your B should be P by 1. So that this transformation is conformable. So we are not talking about here the dimension. The lemma is silent on the dimension, but it is assumed that it is conformable. So if, for example, your A here is, if your A here is n by n, so your matrix vector X here should be n by 1. And this B here, kaya ang result nito is n by 1. So your B here should be n by 1. Are you following? Did you
Yes, ma'am.
understand?
Okay, ma'am. Yes, ma'am.
So as long as in your transformation of your random vector, everything here should be conformable. Okay, so in this proof, I have line 1, 2, 3, 4, 5. Do you have questions on which line? Did you did not understand? Wala? This is okay? Okay. Wala anything. So I will assume that's okay. The proof is okay. Let's look at these definitions here. A symmetric matrix U is non-negative definite, and so this is not U is greater than or equal to 0. This notation in matrix form is telling you that U is non-negative definite, and U will be non-negative definite if this is satisfied. So you can always find a vector n by 1 such that U prime U A is also non-negative. So for this example, A prime U A, when it is symmetric, it is automatically square matrix or square matrix. The same dimension ang rows ug ang column, kay dili siya mahimong symmetric kung P by N siya in general, kay pag transpose nimo ana N by P. So square matrix gina siya basta symmetric. So this is what an n by 1 matrix. So this is n by 1, this is n by n. So this must be n by 1 by n, so that this positive definite here is just a 1 by 1 matrix. So it is non-negative definite if you can find an n by 1 vector, not necessarily constant, no? Such that if you prime multiply U by that vector and post multiply it by that vector, the resulting vector is also non-negative. So if this is non-negative, automatic Q is also non-negative. Also, if you can find an A not all equal to 0 and you pre-multiply it by U, and what you get is it is positive definite, then U is also positive definite, and we write it in this manner. So U is greater than or equal to 0, but this is not read as U greater than or equal to 0, but this is read that U is positive definite. This is read that U is non-negative definite. And as a corollary to 3.1, wherein we know that the covariance of Y with this transformation can be written as A sigma A prime. When it is pre-multiply, again, matrix man to, no? Basta matrix man god, A sigma A prime. Pero kung vector lang, A prime, tungod kay atong transformation gihimo is A prime, small A prime. So if A is an n by 1 vector, then this one is always non-negative definite. So what does this imply? So kung naa kay A na A dimensional, kung imong i-post multiply sa covariance of Y and A, non-negative gyapon siya, this implies that your covariance Y is also non-negative. This is what this definition is telling you. And then this corollary implies that the covariance matrix of a random variable Y is always non-negative definite matrix. Now, when will it be, when will the covariance matrix be positive definite? The next lemma tells you the condition when the variance of Y is positive definite. That is, if Y has a continuous density function, then the covariance of Y will become positive definite. Now, we always want a covariance of Y to be positive definite because we want that the inverse of the covariance of Y, or sigma inverse, exists, no? So when is this true, or when is the covariance of Y positive definite? This is only true if this is satisfied. So if your Y has a continuous density function, then the covariance of Y is positive definite. And the important thing of being positive definite is that its inverse exists. So how do we prove this? We prove this by contradiction. So suppose it's not positive definite. So this is what you want to show. Proof by contradiction starts with suppose it is not true. So P implies Q. So by contradiction is not P implies not Q. So if you can show this, this is proof by contradiction. So what you want is P implies Q. Sayo. Proof by contradiction or contrapositive ba ni? If you want to prove P implies Q, I think contrapositive, not contradiction. By contrapositive, you assume not Q and show it is not P. Let me check. Proof by contrapositive. Tamyan, kay nomdom pa ka sa proof by contrapositive. Correct ba ni? P implies Q. Ang imo ipakita, not Q implies not P. Okay, correct.
Yes, ma'am. Correct,
So,
ma'am.
this is proof by contrapositive. So, lemma 3.2 is a proof by contrapositive. That is, P implies Q. Ang imong ipakita is not Q and then not P. Okay? Can you still see my screen?
Yes, ma'am.
I cannot see my screen. Sige, ingna lang ko. Anyway. Where is my screen? Wala na akong screen. Okay. So this is proof by contrapositive. It's still following, no? Nagsunod pa siya.
Oo, ma'am. Nagasunod pa, ma'am.
Contrapositive. Can you see the word contrapositive?
Yes, ma'am.
Ma'am.
Okay, proof by contrapositive. Ibig sabihin, P implies Q. Ang imuhang himuod sa proof nimo is assume it's not P, then show it's not, assume it's not Q, then show it's not P. Okay, so dinhi na statement, ang P nato is Y has a continuous function. Ang Q nato is Q is positive definite. So now we assume not Q. Okay, so suppose that the covariance is not Q. It's not positive definite. So it's just non-negative. Non-negative, non-definite matrix. Okay, so suppose it's just a non-definite matrix. Or non-definite or not positive definite, no? Then if it's not positive definite, by definition of a positive definite, not non-negative siya, na ay nag-exist na A such that tinuod ni. Okay? So there exists some A, not all zero, such that the variance of A prime Y or the covariance of A prime Y, which is by definition kay isa ra man na ka random variable, variance na siya, is covariance man gud ang iyang gisgot dinhi, but this covariance is actually the variance, no? This is how variance of A prime is equal to, and that is equal to 0, which means that the variance, when the variance is just equal to 0, no? It's just equal to 0, then it's just that random variable is just a constant. So if it is just a constant, then there must exist a constancy such that when you get the probability of AY to be exactly equal to that constant, kay constant man siya, then the probability of that random variable is equal to a constant is 1. You are very sure. Now, but if Y is a continuous density function, kung continuous siya, ang probability na it is exactly equal to a constant is 0 for all C, which is a contradiction. So we have shown that it is not P, no? Which is a contradiction. Then, our assumption na not Q must be wrong. So it must be that P, if Y has a continuous density function, then the covariance matrix is positive definite. Okay? Okay. Pag continuous, kung naa siya continuous function, dapat ang probability na it is exactly equal to a constant is equal to 0, then it's not a continuous function. So if you recall sa inyong basic na probability, when you find the probability under a normal curve, example kinesia, this is equivalent to the probability that x is less than or equal to small x. But the probability that x is exactly equal to small x will be 0. So that the probability that x is less than or equal to 0 is just equal to, for a continuous random variable, which is the probability that x is less than 0 plus the probability that it is equal to 0, but it is equal to x, but the probability that a random variable x is exactly equal to small x, a specific value is equal to 0. So usually when we do continuous distribution, we do not look at mass function, but we look at intervals. Okay, so that is lemma point 3.2. Okay, so by the time we are done with the exam on Tuesday, Thursday we'll talk about the moment generating function. So we will go back on Thursday on the moment generating function. So you prepare yourself for chapter 2 exam. The exam will be, wala may klase buntag, no? Sa Tuesday.